The Artemis II crew wasn't sent to the moon to watch it get hit, but mission timing placed them behind the moon during a once-in-a-generation eclipse geometry, perfect darkness, perfect position, a view no human has ever had. And from that accidental ringside seat, they watched meteoroid after meteoroid slam into the lunar surface. 6 impacts, 57 minutes, each one a silent kiloton-class detonation on a world with no one to feel it. That rate shouldn't be possible, and Earth's data had already been signalling something for months. The American Meteor Society recently acknowledged a measurable shift in the near-Earth meteoroid environment this year. The Artemis crew may have just handed us the first direct evidence of what that shift looks like up close. It doesn't stop there. An asteroid is days away from passing closer to Earth than the Moon. The Sun has been running hot, elevated radiation output for 4 straight days. And the crew who witnessed all of this is now flying home to the fastest crewed re-entry in history, trusting a heat shield that failed its first test. Stay with me, because this is either a remarkable string of coincidences, or it's a signal, and we're only beginning to understand what it means. If this has you hooked, make sure to hit like and subscribe to the Sky Lab so you do not miss the next update as this unfolds in real time. And drop a comment. Where in the world are you watching from? What time is it? And give me your honest gut reaction. Is the crew safe on the way home, or is this the part of the story nobody wants to say out loud? Because that question is coming, and so is everything else. Now, let's get into it. Part 1. The hour that shouldn't exist. 6 flashes of light on a dead, airless rock, 140,000 miles from Earth, witnessed by human eyes for the first time in history. Not photographed, not captured by a telescope, or a sensor array, or a purpose-built monitoring system that took a team of engineers 3 years to calibrate. Seen by 4 people floating in a spacecraft, looking out a window, watching the moon get hit. Let me tell you what that actually means, because I think the scale of it is getting lost in the headlines. It is April 6th, 2026. The Artemis II crew, Commander Reed Wiseman, pilot Victor Glover, mission specialist Christina Koch and Jeremy Hansen, are behind the moon, not orbiting it. Behind it, in the full cone of its shadow, cut off from Earth entirely, experiencing something no human being has experienced since the final Apollo mission, more than 50 years ago. Being genuinely, completely, cosmically far from home, they are not there for the impacts, they are there for the eclipse. From behind the moon, the crew is watching the sun slide behind the Earth, a geometry that produces a solar eclipse lasting 57 minutes, 8 times longer than anything you could ever watch from the ground. The moon has no atmosphere to scatter the light, no haze to wash out the contrast. The darkness is total. The silence is total. And against that perfect blackness, something starts happening on the lunar surface below them. Wiseman reports it first. His words, transmitted back to mission control through the relay satellite that gives them their only thread of contact with Earth, carry something you don't often hear from professional astronauts, who are famously trained to deliver information like machines. He sounds genuinely startled. "We saw at least 5, he says. Then he corrects himself. Maybe 6, maybe more. Victor Glover, watching a different section of the surface closer to the South Pole, confirms another one. 6 impacts. 6 flashes of kinetic energy converted instantaneously into heat, plasma, and visible light. 6 rocks travelling somewhere between 20 and 72 kilometers per second. That's between 45,000 and 160,000 miles per hour, slamming into the lunar surface and releasing energy in the kiloton range, each one equivalent to a small nuclear weapon, each one there and gone in a fraction of a second. And the crew of Artemis II saw all 6 of them with their naked eyes in less than an hour. NASA has been monitoring the moon for exactly this kind of event since 2006. Their Lunar Impact Monitoring Program uses purpose-built telescopes, calibrated CCD detectors, and teams of professional observers to catch these flashes. Their annual count, averaged across nearly 2 decades of observation, is approximately 15 to 20 impacts per year. That works out to somewhere between 1 and 2 impacts per month of active monitoring. Their best detection sessions, under ideal conditions, pick up perhaps 2 to 3 per hour of observation. The Artemis crew saw roughly 6.3 per hour. Now here is where you might reasonably say, well, they had a better view. And you would be partially right, which is why this is interesting rather than just baffling. From behind the moon, the crew could see the entire lunar night side simultaneously. NASA's ground-based telescopes can only observe the crescent of the moon lit by Earthshine, a narrow sliver, maybe 10 to 15% of the surface, on specific nights of the lunar cycle. Artemis had all of it, hundreds of times more surface area exposed. That geometric advantage matters. If impacts are distributed randomly across the moon, and you can suddenly see the whole surface at once instead of a sliver, you should absolutely detect more of them. This is not controversial. The geometry is real and it explains something. But here is where it gets complicated, and where you should sit up a little straighter in your chair, because the geometry alone does not close the case. The human eye is significantly less sensitive than a calibrated CCD detector. Professional telescopes can catch events far below the threshold of what a person can perceive. If anything, the naked eye constraint should suppress the detection rate compared to what a properly equipped ground station would see. Wiseman and his crew should have been missing the faint ones, the borderline ones, the barely there flickers that ground-based systems routinely log. They should have seen fewer per unit of surface, not more, and yet they saw 6 in under an hour. So either those 6 were unusually bright, meaning unusually energetic, or the rate of impacts during that 57-minute window was genuinely elevated beyond what the baseline model predicts. Neither of those explanations is comfortable, because if the impacts were brighter than expected, it suggests objects larger or faster than the average sporadic meteoroid were involved. And if the rate was elevated, it raises a question that scientists are not yet willing to answer definitively, but that this channel is absolutely willing to ask. Was something different about the near-Earth space environment on April 6, 2026? Here is why that question matters. Because while those 4 astronauts were watching rocks hit the moon, something else was already happening back on Earth that was making researchers very nervous, and it started months before Artemis ever left the ground. Part 2, why this shouldn't happen. Before we get to what was happening on Earth, let us spend a few minutes really understanding why the lunar observation is as strange as it is, because I think most coverage of this story has glossed over the technical tension at the centre of it. NASA's Lunar Impact Monitoring Program has been running since 2006. It is not a casual operation. The team uses dedicated telescopes positioned to catch the dark portion of the moon during the crescent phases, specifically the nights when Earthshine illuminates the surface faintly enough that a flash will stand out against it. This constrains observation to specific windows each lunar month, roughly the few days around the new moon when the dark side faces Earth, but is still faintly lit. Outside those windows, you simply cannot see the surface well enough to detect an impact flash. Within those windows, the team typically observes somewhere between 1 and 3 impacts per hour in active sessions. The cumulative annual total, after nearly 20 years of data, averages around 15 to 20 confirmed impacts. Some years are slightly higher, some are slightly lower. The distribution, importantly, is fairly consistent. The rate does not spike dramatically from year to year in the historical record. Against that backdrop, consider what the Artemis crew experienced: 57 minutes, 6 confirmed impacts. That rate, if sustained over an hour of equivalent ground-based monitoring with the same surface area, would represent something genuinely anomalous in the dataset. But here is the part that most people are not talking about clearly enough. The surface area problem is not a small factor, it is a large one. NASA's ground-based program observes roughly 10 to 15% of the moon at any given time during the crescent window. The Artemis crew, from their position behind the moon in eclipse shadow, had line of sight to effectively the entire lunar night side simultaneously. That is potentially a factor of 7 to 10 times more surface exposed to detection. If you correct for that increased surface area, the raw detection rate per unit of surface actually comes down substantially. Some of the apparent excess vanishes when you do that math honestly. Scientists are right to point this out. The geometry is a major confounder, and anyone telling you the 6 impacts are flat out inexplicable without acknowledging the surface area advantage is not giving you the full picture. So why are we still talking about it? Because of the sensitivity problem, which cuts in exactly the opposite direction. Human eyes are not CCD detectors. The human visual system is phenomenally good at a lot of things, but quantitative detection of faint transient light flashes is not one of them. A charge-coupled device in a properly dark-adapted telescope will catch events that are orders of magnitude fainter than what the human eye can perceive at that distance. NASA's monitoring program regularly detects impacts that would be completely invisible to an unaided observer. When you factor in the sensitivity difference, the naked eye constraint should dramatically suppress the Artemis detection rate relative to ground-based systems. The crew should have been seeing only the brightest events, the outliers at the upper end of the energy distribution, and they saw 6. So you have 2 forces pulling in opposite directions. The surface area advantage pushes the expected detection rate up. The human eye sensitivity disadvantage pushes it back down. Whether those 2 factors cancel out cleanly or leave a genuine residual excess is exactly the kind of calculation that requires precise knowledge of the luminous efficiency of lunar impacts, the fraction of impact energy that actually gets converted into visible light. And that number is one of the most poorly constrained parameters in planetary science. Luminous efficiency estimates span roughly 2 orders of magnitude in the scientific literature. Depending on the composition of the impactor and the surface properties at the impact site, anywhere from a fraction of a percent to several percent of the kinetic energy might appear as visible light. That uncertainty is enormous. It means that when you try to back-calculate how big or fast an impactor was from the brightness of its flash, you are working with an error bar large enough to drive a freight train through. This is not a criticism of the scientists involved, it is a genuinely hard measurement problem. But it does mean that the current models of what ground-based telescopes should be detecting may be significantly off. We might be systematically underestimating either the brightness of typical impacts or the size of the objects producing them, or both. And if the models are wrong at the low end, then what the Artemis crew saw might not be anomalously high, it might be revealing the true baseline that our Earth-based instruments have never been sensitive enough to see clearly. That possibility, that we have been undercounting all along, is uncomfortable in its own way, because it means the question of whether the near-Earth meteoroid environment has changed recently becomes even harder to answer. You cannot detect a change if you do not have a reliable baseline to compare against, and that brings us inexorably back to the central thread of this story. If the Artemis observations cannot be cleanly explained by geometry and sensitivity alone, and if the models themselves are too uncertain to resolve the question definitively, then you need an independent line of evidence. You need something that doesn't share any of the same observational biases. Something that tells you whether the meteoroid environment on April 6th, 2026 was genuinely elevated, not just geometrically advantaged. It turns out that something exists, and it has been collecting data since January. Part 3. The eclipse that made it possible. Let us pause on the eclipse itself for a moment, because it is easy to treat it as mere context. The setup that put the crew in the right place to witness the impacts, when it is actually something stranger and more significant than that. No human being has ever watched a solar eclipse from behind the moon, not once. Every eclipse observation in human history, every account going back to Babylonian astronomers, every painting and photograph and breathless newspaper description, every scientific expedition, and every moment of wonder shared between people standing in a field watching the sky go dark, all of it happened from Earth's surface, or at most from low Earth orbit. The perspective was always, us here, moon there, sun behind it. On April 6th, 2026, 4 people experienced the opposite geometry. The moon in front of them, the sun behind the Earth, their spacecraft sitting in the deep shadow cone where the Earth's darkness falls. From that position, the sun does not disappear behind a disk the size of your thumbnail held at arm's length. It disappears behind a planet. The scale is fundamentally different. The totality lasted 57 minutes. For comparison, the longest solar totality observable from Earth's surface in the current era is approximately 7 minutes and 32 seconds, and that only occurs at specific locations along a narrow geographic path. The Artemis crew experienced nearly 8 times that duration. 57 minutes in which the sun was fully blocked and the outer solar corona spread across their field of view with no atmospheric interference, no scattering, no haze. Jeremy Hansen, observing the corona during totality, reported seeing it extend approximately 10 solar diameters outward from the sun's edge. From Earth, even from the best mountain observatories with coronagraphs, observers typically resolve the corona to about 2 to 3 solar radii before the signal is lost in the noise of scattered light. Hansen's observation from behind the moon reached more than 3 times farther into the outer corona. the transition region where the structured solar atmosphere dissolves into the solar wind that permeates the inner solar system. That region, the outer corona, is scientifically important in ways that have nothing to do with aesthetics. It is where the solar wind accelerates from subsonic to supersonic speeds. It is poorly imaged historically precisely because it sits in the observational gap between what coronagraphs on Earth can see and what spacecraft orbiting much closer to the Sun can detect. Every observation of it from a new vantage point carries scientific weight. Christina Koch ran an imaging sequence during totality, capturing the lunar mountains in silhouette against the outer corona. The geometry produced a kind of natural coronagraph, the moon's solid disk blocking the overwhelming brightness of the solar disk itself, while leaving the faint extended corona exposed. Koch's images are the first ever taken of this alignment by humans. They are also, notably, the darkest and most contrast-rich images ever taken of the outer corona from a crewed spacecraft. The darkness matters enormously for the impact detections that were happening simultaneously. Behind the moon, in totality, with no atmosphere to scatter light and no Earth glow washing out the surface, the Artemis crew was sitting inside the most contrast-rich optical environment any human has ever occupied. The lunar surface, lit faintly by Earthshine reflecting off the planet above them, presented as a dark grey disk against which a flash of even moderate brightness would stand out immediately. Reed Wiseman noted something that I think is worth sitting with. He said, and I'm paraphrasing here, that human beings have not evolved to see this. We evolved on a planet with an atmosphere and a sky. Our visual system calibrated itself over millions of years to a world with scattered daylight, ambient glow, atmospheric blurring of distant light sources. The crisp, total, unmediated darkness of lunar space, the kind where a kiloton impact on a rock 100,000 miles away registers as a discrete, unambiguous flash against pure black, is a sensory environment our species has simply never experienced before this mission. That framing is not just poetic. It matters scientifically, because it means that the Artemis crew was not just observing the moon. They were functioning as a calibrated detector placed inside the optimal observing conditions that exist in the inner solar system. The 57-minute eclipse window was not just a beautiful accident of timing. It was, from the perspective of impact detection, a measurement opportunity that ground-based science cannot replicate. And yet, as I said before, the geometry cannot explain everything. The eclipse made detection possible. It created the contrast. It extended the totality long enough for 6 events to occur within a single continuous observation window. But it does not tell us whether the rate of those events was normal. That question requires something else entirely. If the eclipse only improved the viewing conditions without changing the actual meteoroid environment, then the moon should look exactly the same from that vantage on any other night. The question is whether April 6th, 2026 specifically, was different. And to answer that, you have to look at what was happening on Earth at the same time, because Earth, for all its atmospheric clutter and observational bias, has been quietly assembling a dataset that points in a very specific direction. Part 4. The fireball signal nobody could ignore. Let me take you back to January of this year, because the story that the Artemis II crew just added a chapter to didn't start behind the moon. It started in a database. A quiet, unglamorous, deeply important database that most people have never heard of, and that has been patiently recording something unsettling for the last several months. The American Meteor Society has been collecting fireball reports since 1973. That's over 50 years of continuous observation. Observers across the United States and Canada, tens of thousands of registered contributors, submit sightings whenever they see something worth reporting. Not every shooting star. Not the faint streaks you catch at the edge of your vision on a clear night. The big ones. The ones bright enough to cast shadows on the ground below them. The ones that produce sonic booms loud enough to rattle windows and wake people up. The ones that leave glowing trails across the sky that persist for minutes after the object itself has gone. Luminous scars in the upper atmosphere that drift and twist in the high-altitude winds, while people below stand in their driveways with their phones out, not entirely sure what they just witnessed. Alongside those human observers, the organisation runs a network of dedicated all-sky camera systems, automated sentinels positioned to catch events that happen when no one is looking. At 3 in the morning over an empty highway, above a darkened city, across the rural stretches where the observer network thins out. 50 years of data, tens of thousands of contributors, purpose-built hardware. It is one of the best continuous records of energetic bolide activity anywhere in the inner solar system, and in the first quarter of 2026, something in that record changed. Here's how it started. Fireballs with 50 or more witnesses, events bright enough and geographically widespread enough to generate simultaneous reports from large areas at once, roughly doubled compared to the same period in previous years. Double. Not a 10% uptick, not a modest seasonal variation that falls within the normal range of fluctuation. Double. If you saw that number in isolation, without any other context, you would already be paying attention. But the raw count wasn't even the most alarming part. It was the statistical signature underneath it. 4.5 sigma. I want to make sure you actually feel the weight of that number, because it's easy to let sigma values wash over you as abstract jargon. So let me translate it into plain language. The probability of seeing a random fluctuation that large, in a dataset this size, with this many observations over this many years of baseline, is roughly 1 in 170,000. Not 1 in 100, not 1 in 1,000, 1 in 170,000. In science, 3 sigma is the threshold where you sit up and say something might be real here. 5 sigma is the bar that particle physicists set for announcing a discovery, the standard used when you claim you found a new fundamental particle. 4.5 sigma sits right in that territory. It is not a number you explain away with a shrug and a footnote. It is a number that demands an answer. And it wasn't just the frequency that shifted. The character of the events changed too. The fireballs being reported weren't just more numerous, they were more energetic, brighter, longer, louder. The distribution of fireball brightness moved upward across the board, which tells you something important. The objects producing these events were larger, or faster, or both. The sonic boom confirmation rate, the percentage of reported fireballs that were independently confirmed to have produced audible pressure waves at ground level, reached approximately 79% during the anomaly window. That is substantially higher than the typical baseline. And long-duration events, fireballs that remain visible for extended periods as they traverse the upper atmosphere, occurred at roughly 2.5 times the rate seen in comparable previous windows. Think about what that means physically. A long-duration fireball is not a pebble burning up in 2 seconds. It is an object large enough and structured enough to survive its initial atmospheric entry, to keep burning, to keep shedding material, to keep glowing as it drives deeper into the air column. 2.5 times the normal rate of those events is not noise. It is signal. Now. The first thing any responsible scientist does when they see a number like this is try to kill it. You look for the artifact. You look for the explanation that makes the anomaly disappear without requiring anything unusual to have actually happened. And there is a very obvious candidate here, one that the researchers took seriously and examined carefully. The last decade has seen a dramatic expansion in the infrastructure of skywatching. Dashcam penetration has increased enormously across North America. Smartphone camera quality has improved to the point where anyone who happens to be looking at the sky at the right moment has a high-resolution recording device in their pocket. Social media has created amplification loops that turn a single fireball sighting into thousands of posts within minutes, each one potentially triggering additional reports from people who weren't even outside but heard something, or felt something, or just saw the glow. More eyes, more cameras, more ways to report. It is completely reasonable to expect that raw fireball counts would increase over time for no physical reason whatsoever, simply because the reporting network has grown. This is a real confounder. It cannot be hand-waved away. And the researchers didn't hand-wave it away. They specifically modelled the expected growth in reporting infrastructure over the relevant period and asked a pointed question. Does the 4.5 sigma anomaly survive after you account for the dashcam effect? Does the signal persist when you correct for the known expansion of the observer network? It does. The 4.5 sigma result is there after correction. The anomaly is not explained by more cameras. Something in the physical data, in the actual rate and energy of objects entering Earth's atmosphere, shifted in the first quarter of 2026 in a way that exceeds what the growth of the reporting network can account for. And then there is the spatial signature. This is the detail that I find most interesting, and that I think has been most underreported in coverage of this story. The surge in fireballs wasn't distributed randomly across the sky. It showed a concentration associated with something called the anthelion source, the region of the sky located directly opposite the Sun, from which a class of sporadic meteoroids arrive on relatively slow, low-inclination orbits that intersect Earth's path from a specific direction. The anthelion source is not new. It is not exotic. It is a well-characterized, well-understood feature of the sporadic meteoroid complex, the background population of debris that permeates the inner solar system independent of any named meteor shower. Objects from the anthelion source have been hitting Earth for as long as Earth has existed. They are the background hiss of the system, the constant low-level bombardment that planetary scientists use as a baseline when they talk about average impact rates. The fact that the anomaly concentrates there is important for a reason that might seem counterintuitive at first. It actually makes the signal harder to dismiss, not easier. If the fireball surge were coming from some exotic new direction, some unusual orbital trajectory that doesn't match any known population, you might reasonably suspect a single large object fragmenting on an unusual path, or some other one-time event with an obvious source. But the anthelion concentration tells you that what changed wasn't the arrival of something novel. What changed was the density. The background population, the existing sporadic complex, the debris that's always been there, appears to have elevated in that region. The background noise of the inner solar system turned up. That is a different and in some ways more unsettling conclusion. It doesn't point to a single identifiable culprit. It points to a structural change in the debris environment. Something that was already there, now present in higher concentrations, arriving from a direction consistent with the existing architecture of the solar system's small body population. Which brings us to the fundamental problem with Earth as a detector. Earth is, scientifically speaking, a terrible place to measure meteoroid flux. The atmosphere filters everything, small objects burn up entirely, medium objects fragment unpredictably, and the energy that actually reaches the surface is a fraction of what arrived at the top of the air column. The observer network is geographically and demographically biased, concentrated in the northern hemisphere, in populated regions, among people who are awake and outdoors and looking upward. Daytime events are systematically invisible. Events over oceans are systematically invisible. Events over polar regions are systematically invisible. What you need to confirm whether what the AMS data is showing is a real physical signal and not an elaborate artifact of atmospheric physics and human observation patterns is a detector with none of those problems. No atmosphere, no geographic bias, no dash cam effect, no social media amplification, no size threshold below which things burn up and disappear. A detector that simply sits in the same near-Earth environment as our planet, intercepts the same flux of incoming debris, and records every single hit with complete fidelity, regardless of the time of day, regardless of whether anyone is watching, regardless of how big or small or fast or slow the impactor is. That detector exists. It has been sitting in the same orbital neighborhood as Earth for 4.5 billion years. It is approximately 2,000 miles in diameter, completely airless, covered in a surface that preserves every impact it has ever received. And as of last week, it had 4 human beings watching it from a distance of 140,000 miles, and it was getting hit. Part 5. The Moon as the Control Group. I want you to stop for a moment and think about how you picture the Moon, not scientifically, just instinctively. When the Moon comes up in conversation, in a song, in a poem, in the background of a photograph, what is it doing? It is hanging there. It is glowing. It is reflecting light it didn't generate, illuminating nights it didn't create, pulling at tides it doesn't think about. It is scenery. It is backdrop. It is the oldest prop in the history of human storytelling, present in every culture that has ever existed on this planet, almost always in a passive role. The thing that is looked at, never the thing that is looking. That instinct is understandable. It is also, in the context of this story, exactly wrong. In the context of the question we are trying to answer right now, has something changed in the near-Earth meteoroid environment in early 2026? And is the AMS fireball anomaly a real physical signal or an elaborate artifact of how humans observe things? The Moon is not scenery. The Moon is not backdrop. The Moon is the most important scientific instrument in the solar system, And I do not mean that loosely or poetically. I mean it in the precise technical sense that a scientist would mean it. It is a detector, a passive, unbiased, atmosphere-free, observer-independent, continuously operating detector that has been sitting in the same orbital neighbourhood as Earth for 4.5 billion years, intercepting the same debris flux and recording every single hit without complaint, without error bars introduced by atmospheric physics, and without any of the observational biases that make Earth such a deeply frustrating place from which to measure the meteoroid environment. To understand why that matters, you need to understand just how bad Earth actually is at this job. Let's start with the atmosphere. When a meteoroid hits Earth, when a rock travelling at 20, 30, 40 kilometers per second encounters the top of our air column, it doesn't simply arrive. It interacts. It compresses the air in front of it faster than that air can move out of the way, generating temperatures that can exceed those on the surface of the Sun. The rock ablates, it sheds mass, it fragments, it decelerates violently. Small objects, anything below roughly a metre or so in diameter, often burn up entirely before reaching the surface. They convert themselves into light and heat and a brief streak across the sky, and then they are gone. Their kinetic energy absorbed by the atmosphere, their physical remains dispersed as microscopic particles drifting slowly downward. Medium objects fragment. They break apart under thermal and mechanical stress, scattering debris across a wide area, arriving at the surface, if they arrive at all, as a collection of pieces rather than a single impactor. The atmosphere is doing this continuously. Every day, thousands of tons of extraterrestrial material enter Earth's atmosphere, and most of it never reaches the ground in any recognizable form. The atmospheric filter is severe, and inverting it, working backward from what you observe at ground level or in the reporting network to determine what actually arrived at the top of the atmosphere, requires models that carry enormous uncertainties, particularly at the size ranges most relevant to this story. When you see a fireball, you are not seeing a rock. You're seeing a rock's interaction with a column of air. The rock itself is largely gone by the time the light reaches your eyes. Everything you can measure, the brightness, the duration, the spectrum, the terminal altitude, is a downstream consequence of a complex hypersonic interaction that scrambles the original signal in ways that are genuinely difficult to unscramble. The atmosphere is not a window, it is a translator, and like all translators, it introduces its own voice into the text. Then there is the observer problem. The population of people who report fireballs is not randomly distributed across the Earth's surface. It never has been. It is concentrated in the Northern Hemisphere, specifically in North America, Europe, and parts of East Asia, in places with high population density, high smartphone ownership, active amateur astronomy communities, and cultural habits that include paying attention to the sky. If a substantial fireball enters the atmosphere over the North Atlantic Ocean at 2 in the morning, the number of reports it generates is approximately 0. The same fireball over Chicago generates thousands. That is not a small correction. That is a fundamental structural bias in the entire dataset, and it means that what the AMS database actually measures is not the global meteoroid flux. It is the meteoroid flux over populated areas in the Northern Hemisphere, filtered through the reporting behaviour of people who happen to be awake and outdoors and looking upward. Daytime events are systematically invisible, regardless of their size, because the sky is too bright to see them against. Events over oceans are systematically invisible. Events over the polar regions, over the Sahara, over the vast emptiness of the Pacific, over Antarctica, invisible. The geographic and demographic bias in the reporting network is so large that correcting for it requires assumptions that are themselves contested. Researchers do their best. The AMS team is rigorous and careful and has been doing this for decades. But the instrument they are working with, human observers distributed unevenly across a planet wrapped in atmosphere, is, by its nature, a deeply imperfect detector. Now consider the Moon. No atmosphere. That is the first and most important difference, and it cascades into everything else. When a meteoroid arrives at the Moon on a collision trajectory, there is nothing between it and the surface. No air column to ablate it. No atmospheric filter to destroy small objects before they can be counted. No hypersonic interaction to complicate the interpretation of the signal. The object arrives, it hits. It deposits its full kinetic energy directly into the impact site in a fraction of a second, producing a flash of light, a pressure wave through the regolith, and a crater whose size and depth encode the energy of the impact with a directness that atmospheric entry never allows. Every impactor of any size that arrives on a collision trajectory completes that trajectory. The moon does not filter. The moon does not burn things up. The moon does not let anything escape by breaking it apart in the air. No observer bias. The moon does not have a social media account. Its impact rate cannot be inflated by a news cycle, or a dashcam boom, or a trending hashtag, or the fact that more people have smartphones than they did 10 years ago. It does not matter whether anyone is watching. The impacts happen regardless. The craters accumulate regardless. The flashes of light occur whether or not a spacecraft happens to be in position to detect them. When we do observe lunar impacts from ground-based telescopes, from orbiting spacecraft, from the naked eyes of 4 astronauts in exactly the right position, we are not measuring a reporting rate. We are measuring an actual physical event rate. There is no filter between the observation and the phenomenon, no geographic bias. The moon is a sphere, and impacts can occur anywhere on the hemisphere facing the observer. From a spacecraft positioned behind the moon during an eclipse, as Artemis II was, the entire lunar night side is simultaneously exposed. Every square kilometre of that hemisphere is equally available to be hit, and any hit that produces enough light to exceed the detection threshold will be recorded. There is no ocean equivalent on the moon. There is no uninhabited polar region that falls outside the coverage area. The surface that is visible is the surface that is monitored, completely and without exception. This is what scientists mean when they talk about independent cross-validation. The AMS database and the Lunar Impact Record share no observational biases. They do not share an atmosphere. They do not share an observer network. They do not share a reporting infrastructure or a dashcam penetration rate, or a social media amplification loop. If both of those detectors, with their completely different error profiles, show elevated signal in the same window, if Earth's atmosphere is producing more energetic fireballs at the same time, that the lunar surface is absorbing more naked-eye visible impacts, then the probability that both signals are independent artifacts drops dramatically. Not to zero, but dramatically. And here is where I need to be honest with you, because this story deserves intellectual honesty more than it deserves manufactured drama. 6 impacts in 57 minutes is a small sample. It is not a definitive dataset. The statistical weight of the Artemis observation, taken completely in isolation, is not sufficient to confirm or deny a flux increase on its own. What it can do, what it does do, is serve as an independent directional signal. A second witness, pointing in the same direction as the first, with a completely different vantage point and a completely different set of potential errors. In a court of law, one witness can be mistaken or biased. 2 independent witnesses who have never communicated describing the same event from different positions is a different category of evidence entirely. The Artemis II crew was not sent out there to study meteoroid flux. Nobody planned this. Nobody designed an experiment. 4 human beings ended up in the most unobstructed observational position any person has ever occupied in the history of our species, behind the moon, in total darkness, during a 57-minute window of perfect contrast, and they watched the surface get hit, repeatedly, at a rate that, even accounting for their geometric advantage, raises questions that the existing models struggle to answer cleanly. The question of whether the near-Earth meteoroid environment changed in early 2026 is no longer a question that only ground-based detectors are weighing in on. 4 humans, 380,000 kilometers from home, just added their testimony to the record, and unlike every other witness in this story, they had a completely unobstructed view. Part 6. The rate problem no one wants to touch. Let's talk about the number that nobody in mainstream coverage wants to sit with for too long. Because there is an implication buried in the arithmetic of what the Artemis II crew observed that is genuinely uncomfortable. Not in a sensationalist way, not in a the skiers falling way, but in the quiet, specific way that a number sometimes is when it doesn't match the model it's supposed to fit. 6 impacts. Naked eyes. Under an hour. To understand why that is uncomfortable, you need to think carefully about what it actually takes to see an impact flash on the moon with the human eye. Because the crew wasn't operating in ideal laboratory conditions. They weren't staring at a blank black surface with 0 background illumination. The moon during the eclipse was lit by Earthshine. Faint light reflected from Earth's surface and atmosphere back onto the lunar night side, giving it a soft, diffuse grey glow. It is genuinely beautiful. Astronauts and photographers love it. But from an impact detection standpoint, it means there is a background brightness level that a flash has to overcome before the human visual system can register it as a discrete event. Below that threshold, nothing. No matter how many rocks hit the surface, no matter how many kilotons of energy get deposited into the regolith, if the resulting flash doesn't clear that brightness bar, the crew sees grey. Just grey. An unbroken, featureless disk of reflected Earthlight. Above that threshold, something very different. A point of light. Instantaneous, localized, unambiguous, there and gone in a fraction of a second, leaving no trace on the surface visible from that distance, but burning itself into the memory of whoever was watching. That is what 6 times means. 6 events that cleared the threshold. 6 flashes bright enough to register in human vision at lunar distance against an Earthshine background without any optical aid whatsoever. The question that flows directly from this is both simple and scientifically important. How much energy does it take to produce a flash that bright? This is where the calculation gets interesting, and where it gets deeply uncertain in a way I want to be honest about, because the uncertainty is not a minor footnote. It is central to everything that follows. The key variable is something called luminous efficiency. The concept is straightforward. When a meteoroid hits the lunar surface at hypersonic velocity, when something travelling at 20, 30, 40 kilometers per second suddenly stops, the kinetic energy has to go somewhere. Most of it goes into heat, pressure waves through the regolith, excavation of the crater, ejection of material. But some fraction of it gets converted into visible light. That fraction is the luminous efficiency. A high luminous efficiency means a small object can produce a very bright flash. A low luminous efficiency means you need a much larger, faster object to generate the same brightness. The entire energy calculation, the entire effort to work backward from a flash to an impactor size, depends on this number. Here is the problem. Luminous efficiency for lunar impacts is one of the most poorly constrained parameters in planetary science. Current estimates in the published literature span roughly 2 orders of magnitude. That is not a typo. 2 orders of magnitude means a factor of 100 between the low end and the high end of the accepted range. To make that feel concrete, if I told you that a journey takes somewhere between 1 hour and 100 hours, that range would be useless for planning anything. The luminous efficiency range is approximately that useful for precise energy calculations. Researchers have been working to narrow it for years, and there has been genuine progress. But the fundamental difficulty is that you cannot run controlled experiments at the relevant velocities and scales in a laboratory setting. You're always working backward from observations that carry their own layers of uncertainty. With all of that caveat firmly in place, and I mean firmly because this matters, what the best current estimates suggest is that the impacts visible to the naked eye at lunar distance, under eclipse conditions, were likely releasing energy in the kiloton range, not megatons. Kilotons, the lower end of nuclear weapons yields. For reference, the Hiroshima bomb released energy equivalent to roughly 15 kilotons. The events the Artemis crew witnessed were probably at the lower end of that scale, perhaps 1 to a few kilotons each, but they were in that general territory. Silent, instantaneous, a frame of light on a grey surface and then nothing, no mushroom cloud, no shock wave through an atmosphere that doesn't exist, just a crater that wasn't there before, and 4 humans 140,000 miles away who caught the moment it was made. That energy level corresponds, under current models, to objects roughly 1 to several meters in diameter, travelling at the typical velocities of sporadic meteoroids, somewhere between 20 and 40 kilometers per second, depending on the orbital geometry of the specific impactor. And this is where the story stops being purely about what the crew witnessed and starts being about what it implies for the broader picture. Objects in the 1 to several meter size range are not micrometeoroids. This point is worth making explicitly because there is a tendency in casual coverage of space impacts to blur together everything from interplanetary dust to house-sized asteroids under the general label of space rocks, which does nobody any favours. The grains of sand, the submillimeter fragments, the microscopic particles that constitute the overwhelming majority of the meteoroid flux by sheer number, those are not what we're talking about. The Artemis crew was not watching dust settle onto the lunar surface. They were watching the upper end of the small impactor population. The objects in the size range that, if they had arrived at Earth instead of the Moon, would have done exactly what the American Meteor Society was already documenting in its anomaly data: produced significant fireballs, generated sonic booms, potentially rained fragments onto the ground below. This is the connection that makes the two signals, the AMS fireball surge and the Artemis impact observations, so mutually reinforcing when you look at them together. They are not just happening at the same time, they are implicating the same size range, the same population of objects, the same part of the near-Earth debris environment that happens to be the least well understood and the most difficult to characterize. Which brings me to the uncomfortable truth about the models. The models we use to plan planetary defense, to estimate impact frequencies, to decide where to point our detection telescopes and how to prioritize threats, were built primarily from observations made from Earth through Earth's atmosphere, using instruments with specific sensitivity thresholds and specific geographic coverage areas. Those models are genuinely good at the large end of the size distribution. Objects bigger than 100 meters or so can be imaged directly by survey telescopes, tracked across multiple nights, and added to the catalogue with reasonable completeness. The Planetary Defense Coordination Office exists precisely to track those objects, and it does the job well for the size ranges where the instruments work. The models are also reasonably good at the very small end, objects smaller than a few centimeters, which leave their record in recovered meteorites, in the microcrater record preserved on lunar samples returned by Apollo, in the continuous background hiss of the atmospheric entry data. The tiny stuff is well characterized. The gap, the dark zone in our knowledge, sits between roughly half a meter and 10 meters in diameter. Objects in that range are too small to show up reliably in most asteroid survey systems. They don't reflect enough light to be consistently detected at the distances where you would want to find them, far enough away to give you any warning time, but they are nowhere near too small to matter. An object 5 meters across hitting Earth's atmosphere at sporadic velocities does not burn up harmlessly at altitude and leave a pretty streak across the sky. It produces a substantial fireball, possibly a pressure wave, possibly ground-level fragments. The Chelyabinsk event, which you may remember from 2013, involved an object estimated at roughly 20 meters, and that object was detected by the global asteroid detection infrastructure exactly 0 times before it entered the atmosphere over Russia and injured more than 1,000 people. 0 detections, complete surprise, and that was 20 meters. The size range implicated here is smaller, which means even harder to detect, which means the catalogue is even less complete. Now, there is a less alarming version of this, and intellectual honesty requires me to give it to you. The sporadic meteoroid complex, the diffuse background population of debris filling the inner solar system, may not be uniform in time. It is entirely possible, and some researchers consider it likely, that the complex has structure, density variations, temporary concentration zones produced by the recent fragmentation of a small asteroid somewhere in the system, an object that broke apart weeks or months ago, scattering its debris along its orbital path, that debris now sweeping through the Earth-Moon region as an elevated density wave before gradually dispersing back into the background noise. That word temporary changes the picture considerably. If the Q1 2026 anomaly is a wave rather than a tide, a short-duration pulse rather than a permanent shift in the baseline debris environment, then the implications are more limited. Not zero, but more limited. The neighbourhood hasn't fundamentally changed. A denser than usual patch of debris passed through, left its fingerprints in the AMS database and on the lunar surface, and moved on. The wave dissipates. The baseline returns. We file the observation, update the models, and move forward with a slightly better understanding of how lumpy the sporadic complex actually is. The problem is we do not have a confirmed source. No fragmentation event has been identified. No parent body has been flagged. The wave hypothesis is consistent with the observations. It fits the data, but it is not confirmed by the data. It remains, for now, the most plausible, benign explanation for a signal that does not yet have a definitive cause. What we are left with is exactly this: a statistically robust anomaly in Earth's fireball record, a burst of naked-eye lunar impacts in the same window, a size range implicated by both signals that sits in the least understood part of our near-Earth object catalogue, and a calculation, uncertain, caveat heavy, but not dismissible, suggesting that the objects the Artemis crew watched strike the moon were depositing kiloton-scale energy into the lunar surface, silently, repeatedly, while 4 humans floated in the dark and watched. A wave rather than a tide. Maybe. But a wave real enough to leave new craters on the moon while people were watching it happen. Part 7. The asteroid that crosses the line. 3 days after the Artemis II crew watched 6 rocks hit the moon, an asteroid passed between Earth and the moon. Let me say that again, because I want you to feel the geography of it. Not past Earth, not past the moon, between them, inside the moon's orbital distance, in the space that we think of, loosely and perhaps too comfortably, as our immediate neighbourhood, the volume of space that contains our only natural satellite, our GPS networks, our communication infrastructure, the orbit that humans have now twice travelled to reach. Inside that space, on April 9th, 2026, a rock the size of a house passed through without anyone on the ground feeling a thing. The object is designated 2026 GD. It is approximately 10 to 20 metres in diameter, so we're talking about something in the range of a 3 to 6 story building, depending on where in that size estimate the truth lands. It passed at a distance of roughly 155,000 miles from Earth. The moon's average distance from Earth is about 239,000 miles. That means 2026 GD came through at approximately 65% of the lunar distance. In the formal language of planetary science, this is called a sublunar distance approach, a close flyby that occurs inside the moon's orbital path. Now, I want to be absolutely direct about what this means and what it does not mean, because this is exactly the kind of data point that is easy to present irresponsibly, and I am not going to do that. 2026 GD was not dangerous. It is a well-tracked object. Its trajectory was known well in advance. The geometry of its approach was fully determined, the margins were comfortable, and at no point did anyone with access to the actual orbital data have any concern about an impact. Nobody was at risk. Nothing dramatic happened. The asteroid came through, continued on its orbital path, and is now receding from the Earth-Moon system on a trajectory that takes it nowhere near us for the foreseeable future. If you're waiting for me to tell you it was a near miss, I am not going to, because it wasn't. It was a flyby, a close one by everyday standards, an unremarkable one by the standards of planetary defense monitoring. Sublunar distance approaches happen several times a year. The catalogue of known near-Earth objects is full of small bodies that thread through the Earth-Moon system on their way around the Sun, most of them posing no risk, most of them tracked well enough that their paths are known with high confidence. This is not unusual. The solar system is full of small rocks, and some of them pass close to Earth on a regular basis. That is simply the reality of living in a planetary system with a complex debris environment. So why are we talking about 2026 GD? Because of when it happened, and because of what else was happening at the same time, 3 days. That is the gap between the Artemis II crew documenting an elevated impact rate on the lunar surface and a 10 to 20 metre asteroid threading through the space between Earth and the Moon. And 2026 GD was not alone. In the same 2-week window surrounding the Artemis eclipse transit, several other small asteroids passed within 5 lunar distances of Earth. Not one, several. None of them dangerous. All of them tracked. All of them proceeding on their predicted trajectories with no drama and no risk. But here is the thing about context. Individual events examined in isolation are almost always explicable. A fireball over North America, explicable. 6 impacts on the Moon in an hour, geometrically advantaged, possibly explicable. An asteroid passing at sublunar distance happens several times a year, explicable. The radiation environment spiking from a coronal hole stream, routine space weather, explicable. Each one, alone, has a comfortable individual explanation that fits within the normal range of variation in the near-Earth environment. What is harder to explain comfortably is all of them together, in the same window, pointing in the same direction. The asteroid catalogue does not show a permanent increase in object density. Space has not suddenly become more crowded on any timescale that matters for long-term planetary defense planning. What it shows, during this specific window in early April 2026, is a temporary clustering. A momentary alignment of orbital paths that brought multiple small objects from microscopic meteoroids all the way up to the house-sized 2026 GD through the Earth-Moon region at roughly the same time. And temporary clustering, it turns out, is one of the least well-understood features of the near-Earth object environment. The classical model of the near-Earth object population, the one that underlies most of our planetary defense planning, most of our risk estimates, most of our decisions about where to point detection telescopes and how to allocate resources, treats the population as a more or less uniform flux. Objects arriving independently, on uncorrelated orbits, distributed randomly in time. On long time scales, years to decades, that model works reasonably well. The average impact rate is relatively stable. The background fireball frequency follows predictable patterns. The catalogue of large objects grows steadily as surveys accumulate observations. The model is not wrong. It is just a simplification, and like all simplifications, it breaks down at the edges. The edge where it breaks down most noticeably is short timescales, days to weeks. At that resolution, the question of whether close approaches and impacts cluster in time, whether the near-Earth debris environment has temporary density enhancements that sweep through the Earth-Moon region and produce elevated rates of detectable events for brief windows before dissipating, is not settled. It is actively debated. There are researchers who think temporal clustering is real and significant. There are researchers who think it is mostly a statistical artifact of small samples and human pattern recognition. The data needed to resolve the debate definitively is hard to collect, precisely because the events in question are brief, distributed across multiple detection systems with different biases and difficult to link causally even when they are observed. Here is the hypothesis that the convergence of signals in early April 2026 most naturally suggests, stated as clearly as I can state it. The sporadic meteoroid complex, the diffuse background population of debris that fills the inner solar system, may contain coherent structural features, not random, uncorrelated objects distributed uniformly in space, but streams, clusters, density enhancements, regions where material is more concentrated than the background average, moving through the inner solar system together on roughly similar orbital paths, perhaps because they share a common origin. If a small asteroid fragmented somewhere in the system, months ago, a year ago, far enough back that the debris has had time to spread along the orbital path but not so far back that it has fully dispersed into the background, the resulting debris cloud would not be uniformly distributed in space. It would be a coherent structure, elongated along the orbital path, sweeping through the Earth-Moon region, over a period of days to weeks as Earth's orbit intersects it. If that is what happened in early April 2026, then the events we have been discussing are not independent. The AMS fireball surge, the elevated flux of energetic bolides entering Earth's atmosphere in Q1 2026, would be the small end of the debris distribution, the countless sub-meter fragments and meter-class objects burning up or slamming into the ground. The Artemis II impacts, the 6 naked-eye flashes on the lunar surface in 57 minutes, would be the same population hitting a different detector, the Moon intercepting its share of the same elevated flux. And 2026 GD, 10 to 20 meters, passing between Earth and the Moon 3 days later, would be the largest tracked member of that same loosely associated group. The biggest fragment from the same fragmentation event, or at least a fellow traveller in the same orbital neighbourhood, arriving in the Earth-Moon system as the tail end of the passage. That is a speculative hypothesis. I want to be clear about that. The data does not prove it. No parent body has been identified. No fragmentation event has been confirmed as the source of the Q1 2026 signal. The orbital data for 2026 GD has not been publicly linked to the AMS anomaly by any research team, and I am not claiming it has. What I am saying is that the hypothesis is consistent with the observations. It fits the pattern. It is the kind of speculation that is motivated by the convergence of independent signals rather than by the desire to tell a dramatic story, and it is worth taking seriously as a framework for organising the data while more analysis is done. But here is the thought I want to leave you with because I think it is the most important one in this entire section. Planetary defence researchers do not lie awake at night worrying about 2026 GD. They know where it is. They know where it is going. It is in the catalogue. It has a designation, a trajectory, a well-determined orbital solution. It is, in the language of the field, a known known. What keeps them awake at night is the size distribution. If 2026 GD is the largest tracked member of a loosely associated group of objects that swept through Earth-Moon space in early April 2026, then by definition there were smaller members of that group that we did not track, objects in the 5 to 10 meter range that passed through the same region on correlated trajectories and were never detected because they are simply too small to show up reliably in the survey systems we use. Objects that, if their orbital geometry had been slightly different, if their path had intersected Earth's surface rather than passing nearby, would have arrived with zero warning, exactly as Chelyabinsk arrived with zero warning, and produced consequences ranging from a spectacular fireball to genuine ground-level damage depending on their size, composition, and entry angle. We saw the ones we saw. The AMS caught the atmospheric entries, the Artemis crew caught the lunar impacts, the tracking systems caught 2026 GD. The ones we didn't see are the ones that matter most, and right now, we have no way of knowing how many of those there were. Part 8. The radiation spike. Let's talk about the part of this story that nobody is connecting to the rest of it. Not because the connection is proven, it isn't, but because the timing is specific enough that leaving it out would be a form of selective storytelling, and you deserve the full picture. From roughly April 3rd through April 7th, 2026, the exact 4-day window that bracketed the Artemis II eclipse transit, Earth-orbiting satellites recorded elevated electron flux levels that exceeded 1,000 particle flux units for an extended duration, with peak values climbing above 6,000 particle flux units. For those of you keeping score at home, that is the kind of reading that triggers alerts at satellite operations centres, prompts space weather forecasters to issue advisories, and causes engineers responsible for high-value orbital assets to start paying close attention to their spacecraft's charging environment. The source was identified quickly. A high-speed stream from a solar coronal hole, a specific well-understood feature of the Sun's atmosphere that had been rotating into a geo-effective position in the days prior, exactly as space weather forecasters had predicted it would. Let me explain what a coronal hole actually is, because the name sounds more exotic than the reality, and the reality is genuinely interesting. The Sun's magnetic field is complex and dynamic. In most regions of the solar atmosphere, magnetic field lines arch upward from the surface, loop outward into space, and then curve back down and reconnect with the surface at another point. Like the field lines of a bar magnet made visible, that architecture traps the solar plasma, holds it close to the Sun, shapes the corona into the streaming structures you can see during a total solar eclipse. It is beautiful, and it is, from the perspective of Earth, relatively benign. But in some regions that appear darker than their surroundings in ultraviolet and X-ray imaging because they are less dense and cooler, the magnetic field lines don't loop back. They open outward, extending out into interplanetary space without reconnecting, creating a direct channel through which solar plasma can escape at much higher velocities than the average solar wind. These are coronal holes, and the stream of fast-moving plasma they produce, the coronal hole high-speed stream, is one of the most reliable drivers of geomagnetic activity at Earth. When a coronal hole high-speed stream arrives at Earth, it compresses the magnetosphere on the sunward side, energizes the radiation belts, drives currents in the ionosphere, and produces the kind of elevated electron flux that the satellites were recording throughout the Artemis window. Geomagnetic storms, aurora visible at lower latitudes than usual, satellite operators watching their spacecraft's surface charging with heightened concern. None of this is rare. Coronal hole streams arrive at Earth regularly, especially during the declining phase of the solar cycle when coronal holes tend to be large and persistent. Space weather forecasters track them routinely. The April 3rd through 7th event was predicted, monitored, and managed without drama by the agencies whose job it is to do exactly that. For most people on Earth, it was invisible. The aurora was lovely at high latitudes. Some radio operators noticed interference. Some satellite operators logged elevated readings and adjusted operations accordingly, and then it passed, as these events always do, and the near-Earth space environment began returning toward its quieter baseline. For the Artemis II crew, it was a different experience entirely. Here is something that tends to get glossed over in coverage of deep space human missions, perhaps because it is not as visually dramatic as rocket launches and moonscapes. The radiation environment beyond Earth's magnetosphere is genuinely hostile in a way that low Earth orbit simply is not. The International Space Station orbits at roughly 400 kilometers altitude, well within the Van Allen radiation belts and well within the protective bubble of Earth's magnetic field. That field deflects a substantial fraction of the energetic particles streaming in from the Sun and from galactic cosmic ray sources. It is not perfect shielding. ISS crews do receive elevated radiation doses compared to people on the ground, and long-duration station missions are managed with that exposure in mind, but it is meaningful protection. The magnetic field is doing real work on behalf of the people inside it. Beyond the Moon, that protection does not exist. The Artemis II crew, during their transit, was operating in the full interplanetary radiation environment exposed to the solar wind, to the elevated electron flux from the coronal hole stream, to the galactic cosmic rays that stream in from outside the solar system and are only partially modulated by the Sun's own magnetic influence. Their cumulative radiation dose for the mission was higher than what ISS crews receive in comparable time periods. Not dramatically, not at levels that approach acute radiation sickness thresholds. NASA manages this carefully, and the crew was never in danger from the radiation itself, but measurably, meaningfully higher. This is one of the known challenges of deep space human exploration, and it is one of the reasons that mission duration and solar activity forecasting matter so much for future long-duration missions to the Moon and eventually Mars. The coronal hole stream that peaked during the Artemis window was not an emergency, but it was an added layer of environmental exposure for 4 people who were already operating in one of the most demanding physical environments any humans have ever occupied. Now, here is where I need to be very precise, because this is the part of the story where it would be easy to overclaim, and I am not going to do that. Elevated electron flux does not cause meteoroid impacts. I want to say that clearly and without qualification. Solar wind particles and rocky debris are physically different things. They arrive at Earth and the Moon through completely different mechanisms. They originate from completely different sources, and there is no well-established causal pathway by which an increase in solar plasma density or velocity produces an increase in the rate at which meter-class rocks arrive in the Earth-Moon system. The radiation event and the impact observations are not the same phenomenon wearing different clothes. They are separate things that happened at the same time. There are, if you go looking in the more speculative corners of the literature, some proposed indirect connections between solar activity and the dynamical state of the small body population. Radiation pressure, the physical force exerted by sunlight on small particles, can alter the orbits of very fine dust grains over long timescales. The Yarkovsky effect, a subtle thermal force that acts on larger objects as they absorb sunlight and re-emit it as heat, can cause slow orbital drift in meter to kilometer class objects over timescales of thousands to millions of years. There are researchers who have explored possible correlations between solar cycle phase and meteoroid flux, looking for indirect connections through the way solar activity shapes the heliospheric magnetic field that partially deflects incoming material. These are real areas of scientific investigation. They are also unproven, contested, and operating on timescales that are very difficult to connect to a 4-day event window. I am not presenting them as an explanation for what happened in April 2026. I am mentioning them because intellectual honesty requires acknowledging that the boundary between no connection and no confirmed connection is worth keeping clear. What the radiation data does tell you is something more straightforward and in some ways more important than a causal connection. It tells you that the space environment during the Artemis window was active, measurably, independently, simultaneously active, across multiple different physical channels at once. The electron flux was elevated. The fireball rate on Earth was elevated. The impact rate on the Moon, by the direct observation of 4 human beings, appeared to be elevated. 3 separate physical phenomena, 3 separate measurement systems, all registering above their respective baselines during the same approximate window. That convergence might be coincidence. The solar environment and the meteoroid environment are largely independent systems, and independent systems can produce elevated readings at the same time without sharing a cause. Just as you can have a rainy day and a traffic jam on the same morning without the rain causing the traffic. Coincidences happen. Temporal clustering of unrelated events is a real statistical phenomenon that human pattern recognition tends to overinterpret. But here is what I keep coming back to. The crew of Artemis II was not operating in a typical space environment during their transit. By multiple independent measures, radiation, meteoroid flux, the broader debris picture painted by the asteroid catalogue for that window, the near-Earth space environment in early April 2026 was not at its average baseline. It was elevated, active, measurably different from a typical week in a way that showed up in satellite data, in ground-based fireball networks, in the direct observations of 4 human beings behind the Moon, and in the orbital mechanics of multiple small asteroids threading through the Earth-Moon system in the same 2-week period. Whether all of those elevations share a common cause, or whether they are independent fluctuations that happen to converge in the same window, is a question that the current data cannot answer. The physics does not yet support a unified explanation. The honest position is that we have several anomalous readings and no confirmed mechanism connecting them. What we can say with confidence is this: those 4 astronauts were in the middle of all of it. 140,000 miles from home, outside the magnetosphere, absorbing a radiation dose that their colleagues on the space station were not absorbing, watching a surface get hit at a rate that ground-based instruments had never documented before, in a week when the near-Earth space environment was, by several measures, more active than usual. And they still had to get home, through a heat shield that had already failed its first test, on a trajectory no crewed vehicle had ever flown before. That part of the story is next. Part 9. The 72-hour compression problem. I want to stop here and lay the full timeline out in one place. Not because the individual pieces aren't compelling on their own, we've spent the last several sections establishing that they are, but because there is something that happens when you see them together, lined up in chronological order, that doesn't happen when you encounter them one at a time. A shape emerges, and I want you to see that shape clearly, and then I want to have an honest conversation about what it does and does not mean. Here is the timeline. Q1-2026. The American Meteor Society database begins showing something anomalous. Fireballs with 50 or more witnesses roughly double compared to the same period in previous years. The statistical signature underneath that raw count registers at 4.5 sigma, a deviation so large that random chance produces it approximately once in every 170,000 observations. The signal survives correction for the known growth in reporting infrastructure. It is not dash cams. The events are not just more numerous, they are more energetic. Sonic boom confirmation rates are elevated. Long-duration fireballs, the ones that stay visible across the sky for extended periods, are occurring at roughly 2.5 times their baseline rate. The spatial signature concentrates at the Anthelian source, the region of the sporadic meteoroid complex associated with objects arriving from the direction opposite the Sun, on low-velocity, low-inclination orbits consistent with the existing debris background. Something in the near-Earth meteoroid environment during the first 3 months of 2026 is registering above its historical baseline. The signal is real, it has survived scrutiny, it is in the data. April 3rd through 7th. Earth-orbiting satellites begin recording elevated electron flux from a coronal hole high-speed stream. Values exceed 1,000 particle flux units for an extended duration and peak above 6,000. 4 straight days of enhanced space weather, driving geomagnetic activity, energizing the radiation belts, producing aurora at lower latitudes than usual, and elevating the radiation exposure of any humans operating outside Earth's magnetosphere. The Artemis II crew, during this entire period, is outside that magnetosphere. They're absorbing a radiation dose that their colleagues on the International Space Station, protected by Earth's magnetic field, are not absorbing. The space environment around them is electrically and magnetically active in a way that shows up in satellite data across the entire near-Earth orbital regime. April 6th. Artemis II enters lunar eclipse. The crew finds themselves behind the Moon, in the cone of Earth's shadow in total darkness, with an unobstructed view of the entire lunar night side simultaneously, a vantage point no human being has ever occupied before. During 57 minutes of totality, they observe 6 meteoroid impacts on the lunar surface, 6 discrete flashes of light, each one representing a kinetic energy release in the kiloton range, each one a rock that has been travelling through the inner solar system on a trajectory that ended in a fraction of a second at the lunar surface. The detection rate is roughly 6.3 per hour. The geometric conditions are the best that have ever existed for this kind of observation. The crew is not equipped for impact monitoring. They are not looking for impacts. They see them anyway. April 9th, asteroid 2026 GD, approximately 10 to 20 meters in diameter, passes between Earth and the Moon at roughly 65% of the lunar distance. No impact risk. Clean flyby. Fully tracked, well-determined trajectory. Comfortable margins. But it is the largest of several small objects that thread through the Earth-Moon system within the same 2-week window, and its size puts it squarely in the range implicated by both the AMS fireball surge and the Artemis impact observations, the poorly characterized gap in the near-Earth object catalogue where objects are too small to track reliably, but too large to be entirely negligible. 4 data streams, 4 independent measurement systems, all registering elevated or anomalous readings within a 72-hour window centered on April 6th, 2026. Now, before you let that shape settle into something that feels like a conclusion, I need to tell you something about the way human minds work. Because intellectual honesty requires me to say this clearly, and to say it before someone else frames it as a debunking. Human beings are pattern detection engines. This is not a metaphor. It is a description of how the human nervous system actually operates at a neurological level. We evolved in an environment where the cost of a false positive, seeing a predator that isn't there, diving behind a rock when there is no threat, was low. You waste a few seconds, you feel slightly foolish, you move on. The cost of a false negative, not seeing a predator that is there, was potentially fatal. Evolution does not reward skepticism when the downside of being wrong is getting eaten. It rewards sensitivity, hair trigger pattern recognition, the ability to construct a threat narrative from ambiguous signals and act on it before the evidence is conclusive. That evolutionary inheritance does not turn off when we sit down to analyze data. It runs continuously, beneath every conscious analytical process, whispering connections between temporally proximate events, whether or not those connections are real. When 4 unusual things happen in the same 72-hour window, the pattern detection machinery in the human brain does not wait for a confirmed causal mechanism before filing them together under a single narrative heading. It does it automatically, it does it instantly, and then the conscious mind inherits a prepackaged story and spends its energy looking for evidence to support it, rather than examining whether the story was justified in the first place. I am telling you this because I am not immune to it, and neither are you, and the honest analysis of the April 2026 convergence requires holding it in mind at every step. The radiation event and the meteoroid impacts are almost certainly independent. Solar plasma and rocky debris are physically different things that originate from different sources, travel through space by different mechanisms, and interact with Earth and the Moon in completely different ways. There is no confirmed causal pathway connecting a coronal hole high-speed stream to an elevated rate of meteoroid impacts on the lunar surface. The timing may be coincidence. The electron flux going up while rocks were hitting the Moon is probably 2 unrelated things happening at the same time, and the human mind's eagerness to link them is a feature of human cognition, not a feature of the physical universe. The asteroid flyby of April 9th was on a trajectory governed by gravitational mechanics that had been evolving for years before the AMS anomaly began. 2026 GD did not arrive in the Earth-Moon system because something changed in early 2026. It arrived because the orbital dynamics of the solar system placed it on that path long before anyone was watching fireball databases or counting lunar impact flashes. The timing relative to the Artemis transit is, most likely, coincidence. These are important corrections to the narrative pull of the convergence, and I want you to actually hold on to them rather than treating them as the obligatory skeptical disclaimer before the dramatic conclusion. The grand unified theory of the April 2026 anomaly window, radiation, impacts, fireballs, asteroid, all connected, all manifestations of a single underlying change in the near-Earth environment, is probably wrong in its most ambitious form. Some of those signals are almost certainly independent. The convergence is partly real and partly narrative, and separating those two components is genuinely difficult. And yet, having said all of that with full sincerity, here is what remains. The AMS signal is real. It has survived statistical scrutiny. It accounts for reporting growth. It is in the data at 4.5 sigma, and 4.5 sigma does not come from nowhere. The Artemis impacts are observationally confirmed. 4 human beings saw 6 flashes on the lunar surface during a 57-minute window, and those observations are a matter of mission record. And those two signals, the Earth-based fireball anomaly and the lunar impact observations, are independent of each other in every way that matters for cross-validation. Different detectors, different physical environments, different error profiles, different observational biases, or in the case of the Moon, essentially no observational biases of the kind that plague Earth-based detection. When two independent detectors with completely different error profiles register elevated signal in the same window, the probability that both are artifacts drops dramatically. Not to zero, but dramatically. The fireball anomaly is statistical. The lunar impacts are observational. When those two lines of evidence point in the same direction, the agreement is not a product of human pattern recognition. It is a measurement result. It exists in the data independently of whether anyone finds the convergence narratively satisfying. What that agreement is not, and this is the precise line I want to draw, is proof. It is not proof that the near-Earth meteoroid environment has permanently changed. It is not proof that a debris cloud swept through Earth-Moon space. It is not proof that April 2026 was historically anomalous in a way that will be visible in the long-term record. It is suggestive evidence. Two independent sources, pointing in the same direction at a level of significance that justifies serious scientific attention and continued monitoring. That is a real and meaningful thing. It is not nothing, but it is not a conclusion. The difference between those two positions, between suggestive evidence and confirmed conclusion, matters enormously for how we respond. Overstate the case and you generate noise, erode credibility, and make it harder for the real signal to be heard when the analysis is complete. Understate it and you miss something that may turn out to be important, dismissing a 4.5 sigma anomaly and a set of unprecedented human observations because the causal mechanism hasn't been confirmed yet. The honest position is narrower and less satisfying than either of those extremes. The Artemis crew saw what they saw. The AMS data shows what it shows. Two independent measurements, in the same region of space during the same approximate window registering in the same direction. Whether they share a cause, or whether the convergence is partly a product of the human mind's insistence on finding patterns in a universe that is under no obligation to provide them, that question is still open. And open questions in science are not the end of the story. They are the beginning of the next one. Part 10. The most dangerous part hasn't happened yet. Everything we have talked about up to this point, the fireball anomaly, the lunar impacts, the asteroid threading past, the radiation environment, the convergence of signals in a 72-hour window, all of it is, in a certain sense, the backdrop, the context. The scientific story unfolding around four human beings who are, while all of this is happening, preparing for the single most dangerous thing they will do on this entire mission. Not the transit to lunar distance, not the eclipse, not the passage through an elevated radiation environment while a coronal hole stream hammered the near-Earth space with charged particles, not watching rocks hit the Moon from 140,000 miles away. Re-entry. Coming home is the most dangerous part. It has always been the most dangerous part. And for the crew of Artemis II, coming home in 2026 carries a specific, concrete, documented risk that did not exist for any previous crewed mission, because the vehicle they are riding has already shown once that something about the way it comes home is not fully understood. Let's start with the physics, because the physics alone is staggering enough to deserve a moment of genuine attention before we get to the engineering problem. The Orion capsule will enter Earth's atmosphere at approximately 25,000 miles per hour, Mach 32. I want to give you some reference points for that number, because I think it is easy to hear it, and nod and move on without actually feeling what it means. A rifle bullet, a high-powered rifle round leaving the muzzle at its fastest, travels at roughly Mach 2.5. The SR-71 Blackbird, the fastest air-breathing aircraft ever built, a machine that was so fast it could outrun the surface-to-air missiles fired at it, cruised at Mach 3.2. Orion enters the atmosphere at 10 times the speed of the fastest plane humanity has ever put in the air. The Space Shuttle, for comparison, re-entered at around Mach 25. Orion is coming in faster than that, because it is returning from lunar distance rather than from low Earth orbit, and lunar return velocity is higher than orbital velocity by a meaningful margin. At that speed, the air in front of the capsule cannot get out of the way fast enough. It compresses, it heats. Not from friction, as the popular explanation goes, but from compression. The same physical process that heats the air in a bicycle pump when you push the plunger down quickly, scaled up by a factor that produces temperatures on the heat shield surface exceeding 6,000 degrees Celsius. That is hotter than the surface of the Sun, not the core, the surface, the photosphere, the part of the Sun that produces the light we see every day. The heat shield on Orion during peak heating is being asked to survive a thermal environment more extreme than the visible surface of our star for several minutes, while 4 human beings sit on the other side of it and trust that it holds. The material doing that job is called avcoat. It is an ablative heat shield, meaning it works by sacrificing itself. The outer surface chars, heats to extreme temperatures, and then erodes away, carrying the thermal energy with it as it ablates rather than conducting it inward toward the crew module. As long as the ablation happens in a controlled, predictable way, as long as the material sheds gradually and uniformly as designed, the crew module behind it stays within survivable temperature limits. The physics of ablation are well understood. AV-coat has been used since Apollo. Decades of testing, analysis, and flight experience back it up. The fundamental engineering concept is not in question. What is in question is something more specific and more recent. During the Artemis I mission, the uncrewed test flight that preceded this one, engineers discovered something that nobody had fully anticipated. When the Orion capsule came home from its lunar orbit test and the recovered heat shield was examined, they found localized material loss at more than 100 discrete sites across the shield's surface. Not the gradual, uniform ablation the models predicted. Something different. In multiple locations, char that should have eroded predictably had instead separated from the surface in chunks, a failure mode called spallation, taking intact, unablated material with it as it went. The shield lost more material than expected, faster than expected, in a pattern that the pre-flight models had not foreseen. The investigation that followed was thorough and serious. The root cause was traced to the skip re-entry trajectory that Artemis uses, a specific flight profile that is itself a consequence of the physics of returning from lunar distance. Here is why the skip exists. When a capsule returns from the Moon, its entry velocity is high enough that a direct steep atmospheric entry would generate g-forces during deceleration that would injure or kill the crew. The solution is a skip maneuver. The capsule enters the upper atmosphere at a shallow angle, bleeds off some velocity through aerodynamic drag, then skips back up out of the atmosphere briefly, like a stone skipping across water, before descending for a second, final entry. This spreads the deceleration over a longer time, keeps the g-forces within survivable limits, and gives the heat shield more time to shed the thermal load gradually. The problem is that the skip maneuver creates a thermal pattern on the heat shield that is more complex than a direct entry. The shield heats, partially cools during the skip phase, then heats again during final entry. That thermal cycling, heating, partial relief, reheating produce stress conditions in the avcoat material that the models had underestimated. The spallation was the result. Not a fundamental flaw in the material, not a manufacturing defect, a gap in the model's ability to predict how the material would behave under that specific sequence of thermal loads. NASA's response for Artemis II was direct. Switch the re-entry profile. Instead of the skip trajectory, fly a direct entry that eliminates the thermal cycling responsible for the spallation events. No skip means no mid-entry partial. Cooling means no reheating cycle, means the specific stress condition that caused the Artemis I problem does not occur. The fix is logical. The engineering rationale is sound. The thermal models have been substantially revised in light of what Artemis I revealed, and those revised models support the direct entry approach with confidence. There is, however, a word in that last sentence that deserves your attention. Models. The direct re-entry profile that Artemis II will fly has never been flown with crew aboard. Not once. It is a trajectory that exists at this moment in simulation data and computational fluid dynamics models and wind tunnel tests and the revised analytical frameworks that the engineering team built in response to the Artemis I findings. All of that work is real. The people doing it are among the most capable aerospace engineers on the planet, working with better tools and more flight data than any team that came before them. The confidence they have expressed in the revised profile is not casual or performative. It is the confidence of professionals who have done the analysis and believe in the result. But former NASA engineers, people who worked on the original avcoat design, who understand the material's behaviour at a level that comes only from years of direct experience, have raised concerns publicly that are worth taking seriously, not because they believe the crew is flying to their deaths. Nobody credible is saying that, but because the timeline between identifying the Artemis I problem and flying crew on the revised profile is short by the historical standards of human spaceflight. Because the root cause of the spallation, while attributed to the skip re-entry thermal cycling, may not be fully characterised in all its details. Because there is a difference between we fixed the thing we identified as the cause, and we fully understand everything about how this material behaves in this environment at this velocity, and that difference, in human spaceflight, is where accidents have historically lived. This is not a reason to ground the mission. Risk cannot be reduced to zero in human spaceflight, and the decision to fly with crew after a documented anomaly is always a judgment call that weighs the evidence for the fix against the cost of delay and the imperative of the program. NASA has made that judgment. The crew has accepted it, because astronauts understand the risk calculus of their profession in a way that most of us do not, and because the alternative is not flying at all. But it is worth sitting with what that judgment means in human terms. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen, the 4 people who went further from Earth than any humans have gone in over 50 years, who watched the moon get hit 6 times in under an hour, who floated in the most extraordinary observational position any human being has ever occupied, are now strapped into a capsule that is about to hit the atmosphere at Mach 32, protected by a heat shield whose behaviour under these specific conditions has never been validated with human lives depending on it. They watched rocks hit the moon from 140,000 miles away. Silent, instantaneous kiloton-scale detonations on a surface with no one to feel them. Now they are the ones going through the fire, and the heat shield standing between them and 6,000 degrees is made of the same material that failed its first test, fixed by models that have never been proven at full scale, on a trajectory that has never been flown with crew. The engineers are confident. They have no other option but to be. And neither do the 4 people trusting their lives to the answer. Part 11. 2 competing realities. We have spent a lot of time in this video building the case, laying out the data, walking through the physics, establishing what the signals are and where they come from, and why their convergence in the same 72-hour window is worth taking seriously. Now I want to do something that science communication does not always do well, and that I think this particular story demands. I want to give you both sides, cleanly, honestly, without putting my thumb on the scale in either direction. Because the data at this point genuinely supports 2 different interpretations, and you deserve to understand what each one requires you to accept, not just the dramatic version, and not just the dismissive one. Let's start with the conservative interpretation, because it is not a weak position, and it deserves to be presented at full strength before we examine where it struggles. The conservative case runs like this. The Artemis II crew occupied an observational position that was so geometrically advantaged, full lunar night-side coverage, total eclipse darkness, unimpeded line of sight from behind the moon, that it cannot be directly compared to anything ground-based monitoring has ever achieved. NASA's Lunar Impact Program observes roughly 10 to 15% of the lunar surface during its active monitoring windows. The Artemis crew had line of sight to essentially the entire visible night side simultaneously. That is a factor of 7 to 10 times more surface area exposed to detection. When you correct the raw detection rate for that geometric advantage, when you ask not how many impacts they saw per hour, but how many they saw per unit of surface area per hour, the apparent excess shrinks substantially. Some of it may vanish entirely depending on the exact correction factor you apply. Add to that the sensitivity constraint. The human eye is not a CCD detector. Professional ground-based systems routinely catch events far below the brightness threshold that the naked eye can perceive at lunar distance. The Artemis crew, without any optical aid, would have been missing the faint events, the borderline flickers, the barely there impacts that ground-based systems log without difficulty. When you account for that suppression, when you acknowledge that the crew was only seeing the brightest, most energetic events, the number 6 starts to look less anomalous and more like a reasonable sample of the high-energy tail of the impact distribution during a standard observation window. Under this interpretation, the American Meteor Society anomaly, while real and statistically significant at face value, may represent a genuine but modest enhancement in fireball activity that sits within the historical range of natural variation. Longer-term data may show that the Q1 2026 spike, when viewed against a multi-decade baseline, is an outlier of the kind that complex systems produce periodically without requiring a special physical cause. The asteroid flyby was a coincidence of timing, orbital mechanics, not debris clustering. The radiation event was solar activity, independent of rocky debris by any confirmed physical mechanism. The apparent convergence of 4 signals in 72 hours is partly real and partly narrative, a product of the human mind's eagerness to find patterns and the media's eagerness to amplify them. In 2 years, the conservative view suggests, when the AMS dataset has a full year of post-anomaly data to compare against, when the Artemis observations have been fully analysed and published, when the asteroid catalogue for that period has been thoroughly examined, the April 2026 window will look like a modest fluctuation in a complex and variable system, unusual enough to be interesting, not unusual enough to require a structural explanation. A footnote, not a chapter. That is a coherent, internally consistent interpretation. It handles the geometry problem well. It is right that the surface area correction is large, and that many analyses of the Artemis data have not applied it carefully enough. It is right that the naked eye constraint suppresses detection, and that comparing raw detection rates between the crew and ground-based systems without accounting for that difference is not valid. It is right that 4.5 sigma anomalies, while rare, do occur in complex datasets and do not always have physically meaningful causes. Now here is where the conservative interpretation runs into trouble. It struggles with the luminous efficiency problem in a way that does not resolve cleanly. If the naked eye constraint suppresses detection, and it does, then the 6 impacts the crew observed were the bright ones, the energetic ones, the events at the upper end of the energy distribution for that observation window. The events below the naked eye threshold, the ones the crew missed, would have been even more numerous. When you account for the full distribution of impact energies, not just the ones visible to the crew, the implied total impact rate during that 57-minute window may still be elevated relative to the corrected ground-based baseline. The suppression argument cuts in both directions, and the conservative interpretation does not always acknowledge that. More importantly, it does not give a compelling account of why 2 completely independent detection systems, one atmospheric, one airless, one relying on human observers embedded in a biased reporting network, one relying on 4 human eyes in the most unobstructed observational position ever occupied, both showed elevated signal in the same window. Coincidence is an answer. It is not a satisfying one when the 2 systems share no error characteristics and when the signal they agree on is the direction of the elevation, not just the fact of it. Now the aggressive interpretation, also presented at full strength, because it too deserves that. The aggressive case runs like this. The AMS anomaly is too large and too robust to be a reporting artifact or a minor fluctuation. 4.5 sigma, corrected for reporting growth, concentrated at the Anthelian source, with a clear upward shift in event energy and duration. That is not noise. That is signal. The Artemis observations, while geometrically advantaged, still require the detected impacts to have been energetic enough to clear the naked eye brightness threshold at lunar distance against an Earthshine background, which means they were kiloton-class events, involving objects in the 1 to several meter size range, not micrometeoroids. The geometry helps, but it does not lower the energy threshold. You still need a real, substantial impact to produce a visible flash. When 2 detectors with completely different error profiles, one that filters everything through an atmosphere, a reporting network, and demographic bias, one that has none of those filters, both show elevation in the same window, the cross-validation logic is powerful. The probability that both are independent artifacts, producing a false positive in the same direction at the same time by coincidence, is substantially lower than the probability that either one is an artifact alone. That is not narrative. That is basic statistics applied to independent measurement systems. Under the aggressive interpretation, the meteoroid environment in near-Earth space was genuinely elevated during early April 2026. The most physically plausible mechanism is a temporary density enhancement in the sporadic meteoroid complex, a coherent region of elevated debris density, possibly produced by a recent fragmentation event somewhere in the inner solar system, sweeping through the Earth-Moon region over a period of days to weeks, before dispersing back into the background. The asteroid clustering in the same window is consistent with this picture. The long-duration fireball signal is consistent with this picture. The size range implicated, 1 to 20 meters, sitting in the least characterized gap in the near-Earth object catalogue, is consistent across all the signals. Here is where the aggressive interpretation runs into trouble. It requires accepting that a real, physically meaningful increase in debris density occurred in near-Earth space, was large enough to manifest simultaneously and detectably in both Earth-based atmospheric observations and direct lunar observations, and then apparently subsided, all without leaving a clearly identified parent body in the asteroid catalogue. No confirmed fragmentation event has been linked to the Q1 2026 anomaly. No specific object has been identified as the source of the elevated flux. The wave hypothesis is consistent with the data, but it is not supported by the data in the stronger sense of being confirmed by it. Consistency is not the same as confirmation, and the aggressive interpretation sometimes blurs that line. Here is what I find genuinely honest to say about both positions, having laid them out as carefully as I can. Neither one is falsified by the current data, and that matters, because it means the question is still open, and open questions deserve continued attention rather than premature closure in either direction. The history of planetary science is not kind to premature closure. The Chelyabinsk event in 2013, a 20-meter object that entered the atmosphere over Russia and injured more than 1,000 people, was detected by the global asteroid monitoring infrastructure exactly 0 times before atmospheric entry. An object the size of a 6-story building, approaching Earth on an impact trajectory, invisible to every telescope pointed at the sky. The Tunguska event in 1908, an object estimated at 50 to 80 meters that flattened 2,000 square kilometers of Siberian forest with the energy of a large nuclear weapon, is still debated in terms of its precise origin, composition and orbital history more than a century later. We do not have a clean, confirmed account of where it came from. These events are not being invoked here to generate alarm. They are being invoked because they are the data points that most honestly characterize our actual relationship with the near-Earth debris environment. That relationship is one of recurring surprise, of objects that were not in the catalogue, not on the models, not anticipated by the systems designed to find them. Of gaps in knowledge that only become visible when something falls through them. April 2026 may have been nothing more than a minor fluctuation, observed at unusually high resolution by 4 humans in an unusually advantageous position. A modest statistical outlier in a complex variable system, amplified by media attention and the human tendency to find meaning in convergence. Or it may have been something more than that. A brief real elevation in the density of the debris field surrounding our world, detected from 2 independent directions by 2 independent systems in a size range where the catalogue is incomplete and the models are least reliable. The honest answer, right now, today, is that we do not know which. And not knowing in this particular domain is not a comfortable place to be. Part 12. The question that doesn't go away. 6 flashes on a silent rock. I want to come back to that image. Not the data, we have spent enough time with the data. Not the sigma values, not the particle flux units, not the luminous efficiency uncertainties, and the surface area correction factors, and the cross-validation logic. Those things matter, and we have given them the attention they deserve. But I want to end where this story actually lives, which is not in a spreadsheet or a preprint paper or a mission debrief transcript. It is in an image. 4 people, floating in the dark behind the moon, watching the surface of another world get hit. Hold that image for a moment before we do anything analytical with it. The moon is not passive. It has never been passive, despite everything our metaphors and our poetry have tried to make it. It is not a lantern hung in the sky for our romantic convenience. It is not scenery. It is an archive, a 4 billion year record of every collision, every impact, every piece of debris that the solar system has thrown at it, since the planets finished forming and the neighbourhood began its long, slow, never quite finished process of clearing. Every crater on the lunar surface is a timestamp. Every basin is a chapter. The Great Dark Plains, the Maria, the seas that early astronomers named with misplaced optimism, are the solidified remnants of impacts so catastrophic they melted the crust and flooded entire regions with magma. The moon does not filter those records. It does not attenuate them. It does not argue with the data or revise the archive to fit a preferred model. It simply receives what the solar system sends it and holds the record in stone, in silence, in the airless dark until something larger comes along and rewrites it. That is what makes what the Artemis II crew witnessed so different from everything that came before it. Every previous observation of lunar impacts, every flash caught by a ground-based telescope, every event logged in NASA's monitoring database, every detection made by the patient, careful, underfunded teams who have been pointing cameras at the moon since 2006 was filtered. Filtered through distance, filtered through atmosphere, filtered through the sensitivity thresholds of instruments that can only observe a narrow crescent of the surface during specific windows of the lunar cycle, filtered through the scheduling constraints and weather interruptions and equipment limitations that make ground-based astronomy a constant negotiation between what you want to see and what the universe will let you see on any given night. That science is real and valuable. It gave us the baseline we have. But it is science conducted through a series of layers, each one attenuating the signal slightly, each one adding its own contribution to the uncertainty budget. The Artemis crew had none of those layers. They were in the room. They were sitting inside the most contrast-rich optical environment any human being has ever occupied, behind the moon, in total eclipse darkness, with no atmosphere to scatter light, no instrument sensitivity threshold to filter out the faint events, no observation window constrained by lunar phase. They had the whole night side. They had 57 uninterrupted minutes, and what they saw in those 57 minutes was 6 rocks complete their final journey. Each one had been travelling through the inner solar system for how long? Years? Decades? Longer? On an orbital path shaped by the gravitational influences of the planets, nudged gradually inward or outward by the subtle thermal forces that act on small objects over long timescales, until the path intersected the moon on April 6, 2026, and the journey ended in a fraction of a second of light. 6 rocks, 6 trajectories terminated, 6 new craters added to an archive that already contains billions. The moon did not notice. It never notices. But 4 humans did, and that fact, that for the first time in the 4 billion year history of the moon being hit by things, members of the species that evolved on the nearby planet were present and watching when it happened, is not a minor footnote in the story of our relationship with the solar system. It is a genuinely new thing. Against the background of everything we have covered in this video, those 6 flashes take on a weight they would not have in isolation. If the Artemis crew had watched 6 impacts on a random Tuesday with no broader context, no AMS anomaly in the months prior, no elevated radiation environment, no asteroid threading through the Earth-Moon system 3 days later, the scientific community would have noted the observation with interest and filed it as a data point for future analysis. Remarkable, certainly. Unprecedented, absolutely, but not urgent. The context changes that. The American Meteor Society's Q1-2026 anomaly, a 4.5 sigma deviation in fireball energy and frequency that survived correction for reporting growth, that concentrated at the Anthelian source, that showed elevated sonic boom rates and long-duration event rates that doubled the baseline, was already in the data before the first astronaut strapped into the Orion capsule. That anomaly was already demanding an explanation before anyone went anywhere near the moon. The Artemis observations did not create the question. They inherited it, and then added a layer of evidence that the question had not previously had, a layer collected from outside the atmosphere, with none of the biases that make Earth such a compromised detector, by witnesses whose testimony cannot be explained away by dashcam penetration rates or social media amplification. So here is what we actually know, stated as precisely as I can state it. The AMS anomaly is real. It is in the data. It has survived scrutiny. It is not a reporting artifact. The Artemis observations are real. They are in the mission record. 4 human beings saw 6 impacts in 57 minutes from the most unobstructed vantage point any person has ever occupied. The asteroid population threading through the Earth-Moon system in the same 2-week window was real, catalogued, tracked, confirmed. The elevated electron flux from the coronal hole stream was real, recorded by satellites, consistent with known space weather mechanisms, independent of both the meteoroid signals and the asteroid catalogue. 4 independent measurements, 4 independent data streams, all registering above their respective baselines during the same approximate period. And here is what we do not know, stated with equal precision. We do not know whether those signals share a common physical cause. We do not know whether the meteoroid environment changed in a durable way, whether April 2026 represents a new baseline or a temporary wave that has already passed. We do not know whether the Artemis detection rate, when fully corrected for geometry and sensitivity by a proper peer-reviewed analysis, represents a genuine excess above the expected sporadic background or falls within the range that the geometry alone can explain. We do not know whether the models we use to characterize the near-Earth debris population are accurate enough in the size range implicated by these observations to detect a real change if one occurred. The papers have not been written, the models have not been updated, the data that would resolve the central question definitively has not yet been collected. What I think is worth saying plainly, what I think this story earns the right to say after everything we have covered, is this. The first humans to travel to lunar distance in 54 years came back with an anomaly. Not a disaster, not a confirmed crisis. An anomaly. A set of observations and measurements that do not fit neatly into the existing model of what the near-Earth environment looks like during a typical week in 2026. Observations that align across two completely independent detection systems in the same direction. That occurred in a part of space no human eyes had ever monitored before, during a window of elevated space weather, 3 days before a sizable rock passed between Earth and the Moon. Any single one of those things in isolation is a footnote, a data point, something to note and file and return to when more data is available. Together they are a question, a specific, pointed, scientifically serious question about whether something in our immediate cosmic neighbourhood shifted in early 2026 in a way that our ground-based instruments were not well positioned to detect and confirm. The conservative view says that question has a boring answer, that the geometry explains most of it, the statistics explain the rest, and in 2 years the Q1 2026 spike will look like a modest outlier in a long dataset, interesting but not structurally significant, the kind of fluctuation that complex systems produce without requiring special explanations. The other view says the question is still genuinely open, that the size range implicated by both the AMS surge and the Artemis detections sits in exactly the most poorly characterized region of the near-Earth object catalogue, that temporary density enhancements in the sporadic complex are physically possible and poorly understood, that 4.5 sigma anomalies do not appear in well-characterized datasets without a reason, and that the reason in this case has not yet been identified. I cannot tell you which view is correct. Nobody can, yet. But I can tell you what the Artemis II crew is doing right now as this video reaches you. They are strapped into a capsule travelling at Mach 32, protected from 6,000 degree plasma by a heat shield made of material that failed its first test, flying a trajectory that no crewed vehicle has ever flown before. They went out past the edge of everything familiar, and they came back with a question that the entire scientific community is now trying to answer. They saw the moon getting hit. Repeatedly. At a time when Earth itself was showing signs of elevated bombardment, and then they pointed their capsule at the thin blue line of atmosphere that separates every living thing on this planet from the vacuum they have been floating in for 2 weeks, and they came home. Was what they saw a rare alignment of normal events, coincidence witnessed by humans for the first time, only because this was the first time humans were in a position to see it? Or was it something else? A signal, a first data point in a story that is still being written, a measurement made by 4 people with naked eyes because every instrument we had was pointed in the wrong direction. The difference between those two answers, between coincidence and warning, between artifact and signal, between the ordinary and the unprecedented, may be something we only understand fully in hindsight. And hindsight, in this particular domain, has a long history of arriving later than we would have liked.